In this video, we're going to cover section 5.2, which introduces a method we use to name enantiomers. So, as we've seen previously, if we have a pair of stereoisomers, we saw earlier that if we had two disubstituted alkenes, they were diastereomers, and we could use the terms cis and trans to identify those individual molecules of that pair. Now we want to apply a similar system to identify each of the enantiomers in an enantiomeric pair. And so the descriptors that we use are the letters, uppercase letters R and S. And they're derived from the Latin words for right and left, which are rectus and sinister. And so the R and S configurations are what we use to describe the arrangement of the atoms around a particular chirality center. And the system is as shown, that we first need to prioritize the groups connected to the chirality center. And by prioritize, what I mean is that we're going to identify the atom directly attached to the chirality center, and we're going to compare the atomic number for each of those atoms directly attached to the chirality center. If we have a tie between two atoms directly attached to the center, then we look at the atoms directly attached to each of those first atoms. And we continually do that until we come up with an order from high to low. And so we'll prioritize the four groups. If necessary, we may rotate the molecules so that we can place the lowest priority group behind the page. It makes it a little bit easier to see the remaining three groups. And then we determine the sequence. And by that I mean we will go from high priority group to the next or second highest priority group and third. And if when we draw our pen connecting those three groups from the perspective that we draw, if we go in a clockwise pattern to the right, we'll refer to that as the R enantiomer. Otherwise, if we end up in a counterclockwise pattern, that is going to the left, we'll assign that enantiomer an uppercase S. So in the first part of our process, we need to prioritize all the four groups connected to a chirality center. So that would also imply that we've identified a chirality center in an organic structure. And as I said, the priority is assigned on the basis of the atomic number of the atom that is directly attached to the chirality center. So when we look at this particular compound, this is our chirality center, and we identify it as a chirality center because there are four different groups attached to it. We have a chlorine atom, we have an ethyl group, we have the hydrogen not being shown, and then we have this oxygen ethyl, we call this an ethoxy group, attached on the right side. Identify that with an asterisk. And the same on the right, we see the mirror image of that particular compound. So this is a pair of enantiomers. So if we look below, the structure on the left is drawn again, but now we're explicitly showing the placement of the hydrogen. Hydrogen will always have the lowest atomic number, it's 1. And so it will always be the fourth group in your list. Now, chlorine having a higher atomic number than either oxygen or carbon, it will be assigned the highest priority group. Again, you're just looking at the first atom. You're not looking at any of the other atoms in a particular substituent. It's the first atom that you look at initially. And so now we're comparing oxygen with that of the carbon in this ethyl group, and oxygen has a higher atomic number than carbon. And so, as you can see, we've assigned the priority of the groups, the chlorine atom being first, the oxygen in the ethoxy group being second, the first carbon in the ethyl group being third, and then finally, hydrogen is your fourth group as we prioritize those groups. Now, when the priority cannot be assigned on the basis of the atomic number of the atoms that are directly attached to the chirality center, then the next set of atoms needs to be considered. So in this example shown below, we've identified our chirality center as this carbon with the hydroxyl group, a hydrogen, and then this alkyl chain as well as this alkyl chain. So if we compare this carbon with this carbon, they're identical in every way. So there are two hydrogens attached to this carbon, two hydrogens attached to this carbon, another carbon, neighboring carbon attached, another neighboring carbon attached. So these two CH2 groups, they're indistinguishable in terms of our priority rules. We have the same atomic number associated with all the atoms, both the carbon atoms and everything attached to it. So then you must move out further from the chirality center to the next carbon atom in each of those respective groups. So attached to this carbon atom, we have a carbon, and there are two hydrogens also attached, which are not shown in our bond line structure. On the left-hand side, for this particular substituent, we have two carbons attached to this carbon, highlighted in green, and a single hydrogen that's not being shown. So once we've identified the groups that are directly attached to these carbons, we can list them from high to low in terms of their atomic number. And we see that the first highest priority group attached to each of these carbons is a carbon in both cases. So there's no dissimilarity. So it's the same. But it's the next comparison. There's a carbon, another carbon attached to this isobutyl group compared to the hydrogen. And so it is this particular difference that gives rise to this group being higher in priority than this group. Okay, so in our ranking, this will be 2 and this will be 3. And the hydroxyl group was 1 and the hydrogen will be 4. Now, if you're assigning priorities and you come across a double or triple bond, then you treat the double or triple bond as 2 or 3 single bonds respectively. So in this example, you see you have this aldehyde functional group. And if we wanted to determine what atoms are directly attached to this carbon for the RS system, we would list the atoms bound to this carbon as being oxygen, oxygen, hydrogen. So there's not 2 oxygens bound to this particular carbon, but this is how the RS system is used to assign priority when double or triple bonds are found in the structure. So once you've assigned the priority to each of the groups attached to the chirality center, it may be necessary for ease of viewing to rotate the molecules so that the fourth priority group, or the lowest priority group, is on the dash. And so as you can see in this example, how it's shown here is that the lowest priority group is coming out towards you. There's nothing wrong with leaving it that way, but when you look at the structure to determine whether or not you are going in a counterclockwise or clockwise direction from your highest to third highest priority group, it's sometimes easier to look at it face on as opposed to from behind the page. And so that's why rotating it can be quite helpful. So you have to imagine that what you're doing here is as you rotate this structure around this imaginary axes, you're rotating it such that this group in front is going to turn and end up in back, and the group that was in back is going to come to the front. And so that's shown here, that group number 1 will rotate around that imaginary axis and come onto the left-hand side, and this group 4 was rotating somewhat in front of us and then ends up on the back on the right-hand side. With this rotation, these two groups are not static, they're also moving. And so as you rotate 4 to the back, 3 goes from the left side to the right. And so if you ever exchange the placement of two groups on a two-dimensional surface, a page, you also have to rotate or exchange the position of the other two groups. Otherwise, what you've done is you've just drawn the other enantiomer, and that will get a little bit confusing when you're trying to name this particular enantiomer. So the textbook goes into detail as to how you can, go about doing this in a simplistic fashion. My suggestion is just, if you exchange the placement of two groups, that you also exchange the placement of the two remaining groups. Not doing so, as shown here, you've redrawn the structure from one enantiomer to the other. So in this example, if we were to assign the configuration of this chiral center, taking our pen starting from our highest priority group, going to our second and then our third, we're taking a counterclockwise rotation. And so this is to the left, and so we would give this the configuration S. If I just exchange two groups around that chiral center and not change anything else, in fact, what I'm doing, as we saw in the last video, by exchanging those two groups, I'm redrawing the structure as the other enantiomer. So this is one strategy that's recommended in the textbook, is that if you want to have the structure drawn as shown with the lowest priority group in behind, what is recommended is that you take the lowest priority group and exchange it with whatever group is in behind the plane. So in this example, you take whatever this group 4, your lowest priority group, you exchange it with the group in back. Then the second step of this process is to exchange the placement of group 1 and group 2. Doing so then, in a sense, redraws the original structure. So these are identical structures. This is not. This is the enantiomer of those two other structures. So if you find it challenging, and it's very common when you're first starting to look at stereoisomerism, if you find it challenging to rotate the molecule kind of in your mind, then this is one strategy that works every time, that you take the lowest priority group, you exchange it with whatever group is in behind the page, and then you exchange the other two substituents off that chirality center. Doing so will give you the rotated structure, the rotation of the original structure that places the lowest priority group in behind. And now when you draw your pen, or take your pen and draw from 1 to 2 to 3, we see in this example that we're going to the right. And so this would be our configuration for this generic cartoonish tetrahedral without any groups. But that's how you would switch the groups such that you can see the structure a little bit more clearly, so that you can assign the configuration as R or S. So the third step is to just determine the sequence, whether going from 1 to 3, are you going in a clockwise manner or a counterclockwise manner? So as shown in both these structures, you can see that here's an example where our highest priority group coming towards you, if we draw our pen from there to our second to our third, we're going in a counterclockwise manner. And so the configuration for this chirality center would be considered S. However, if starting from highest priority group and drawing towards the second and third highest priority groups, if that sequence gives you a clockwise direction, then you would identify that as the R enantiomer, or assign this particular chirality center as having the R configuration. And as shown in a previous example, we will place that information in front of a name in brackets, and we will separate it from the rest of the name with a hyphen. And so if it's the S enantiomer, it's the S in brackets. If it's the R, you place the R in brackets and place a hyphen, and then the rest of the name. So stereo descriptors are literally the last thing that we assign in our naming of organic compounds. So let's look at an example and apply the RS system to it so we can assign the configuration for various chirality centers in organic structures. So in this example, we'll look at ephedrine, which is a bronchodilator and decongestant. And you can see in this example that we have two regions of interest. We notice that there's some three-dimensional bonds associated here as well as here. And so that's a good indication of a potential chirality center, because again, you need to explicitly show the three-dimensionality around a chirality center for you to be able to assign the configuration. If we were to redraw these without those three-dimensional bonds, you wouldn't be able to identify the configuration based on the structure. You need that three-dimensional information in order to assign configuration. So in this example, if we look at this carbon atom, we have a hydroxyl group, we have a phenyl ring, we have a hydrogen not being shown, and then we have the remainder of the molecule. And so yes, we have 4 different groups, and so we will assign this as a chirality center. Neighboring that is another carbon with a 3-dimensional bond to a methyl group, a hydrogen not being shown, the remainder of the molecule on the left-hand side, and then this amino group on the right-hand side. So yes, we have a second chirality center associated with this molecule. What's ideal in this example, and not done on purpose, but what is nice is that in both cases, the hydrogen that is not explicitly shown is behind the page. Now you could draw those in for the purposes of this exercise, and we would draw them in this manner. Something without moving over those 3-dimensional bonds, we could kind of sneak those hydrogens in for our purposes of assigning configuration, not for drawing bond line structures, of course. All right, so let's start with the structure, part of the structure that has a chirality center, which we've identified with this blue asterisk. And so if we want to number the groups in terms of their priority, what we're comparing in terms of the atoms attached to this carbon are the following. We're comparing the oxygen in the hydroxyl group with the hydrogen directly attached to that chirality center. On the right-hand side, we have a carbon center, and on the left-hand side, we also have a carbon center. And so based on just comparing those 4 atoms, we can at least assign the first and fourth priority groups. And so the hydroxyl will be 1, and this hydrogen will be 4. What we can't determine based on the first 2 atoms directly attached to the chiral center is whether the phenyl group takes higher priority over this alkylamine structure on the right-hand side. So we need to then look at what is attached to those particular carbons. So to the carbon of the ring system, what's directly attached to this carbon is a carbon, carbon. But remember, we treat this double bond as yet another single bond to that same element. So this carbon is directly attached to carbon, carbon, carbon. So I can draw that out here. Maybe I'll space this out so it's a bit easier to see. And what's attached to the other carbon would be a hydrogen, a nitrogen, and a carbon. Okay, so now we have a nitrogen in the running, a carbon of that methyl group, and a hydrogen. So when we compare the nitrogen to carbon, nitrogen has a higher atomic number. And so this group, which we use to assign this group, this will be the second highest priority group in our structure for that particular chirality center. So this will be group 2, and the phenyl ring will be group 3. And so when we take our pen and start from the highest priority group, with the lowest priority group in behind the page, 1, 2, 3, we're going in a clockwise manner to the right. And so this particular chirality center will be an R configuration. So let's draw this out here. This will be the R. All right. So let's look now at what I highlighted in yellow as the other chirality center of our structure. So right away, we will assign this hydrogen as our lowest priority group, our fourth priority group. If we look more closely at the structure, the first elements that are bound to that particular chirality center are nitrogen, carbon, and carbon, and of course the hydrogen. Okay? So just based on that first comparison, again, we can assign our fourth and first priority groups. So this will be 1, because nitrogen has a higher atomic number than carbon, and our fourth group will be the hydrogen atom. Now we have to look more closely at the other two. This particular carbon is bound to 3 hydrogens. Whereas the other carbon here is attached to an oxygen, a carbon, and a hydrogen. And so that's all we need to determine our first point of difference. The oxygen atom that's directly attached to that carbon, once removed, if you will, or right next to the chirality center, is higher in atomic number than a hydrogen. And so we can assign this part of the molecule with respect to that other chirality center is 2, and the methyl group will be 3. Okay. So now, if we want to assign the configuration for this chirality center, starting with our pen at 1, going to 2 and 3 with 4 in behind, we're going in a counterclockwise direction. And so we would assign this the letter S for that particular configuration. So this will be our S. So within this molecule ephedrine, we have 2 chirality centers, and the configuration of the chirality center at this location we assigned as R, because we had that clockwise rotation going from our highest priority group to our third highest priority group, whereas the opposite was encountered for that other chirality center. So if you have any questions with respect to the RS system and how to assign the configuration to a chirality center in an organic structure, by all means, send me an email, or we can set up a Zoom appointment, or start a discussion in the forum if you have any specific questions you would like me to respond to. Thank you.